Okay, welcome everyone. Hope you're doing well. Today we have a really interesting question that I think is fun and a bit difficult to wrap our minds around, but we're going to get into it, okay? So the question is called n points on a circle. Given n points drawn randomly on the circumference of a circle, what is the probability that they are all within the same semicircle? Okay, and so here I've drawn a circle and I've randomly placed a bunch of points on the circumference and I've drawn a semicircle. And so what we want to see is that we want to find the probability that all of these points are going to be within this same, or can be found within a same semicircle. Okay? All right, let's get into it. So for questions like this, I think what can be helpful to do is to look at start and end states. Okay? So let's envision the start state of our circle. What is that going to look like? It's just going to be an empty circle like this, right? It's not going to have any points on it. The circle is untouched by the points, right? And on the end state, right? On the end state of the circle, we've placed our endpoints, right? The circle is riddled with the endpoints which we have placed. Maybe there's one here, maybe there's one here, maybe there's one here and here. And we're trying to find what is the probability, that all these points are going to fall within the same semicircle. And so when I look at these two images, which one is going to be more helpful for me to start approaching the problem? And I don't think it's going to be the one in the end state, because I'm kind of looking at this and I'm not sure where to start. I mean, I could draw a semicircle here, I could draw a semicircle here. I'm just not really sure where I should go with this. So for that reason, I want to look at the start state, okay? Okay, so I'm going to begin by redrawing our start state, okay? So the start state is this empty circle, right? And we have n points, right? There's n points we need to place on this circle. So let's just begin by placing one of our points, okay? And I'm just gonna, place it right up here for the sake of generalization. It doesn't really matter where I place it because all points on this circumference have an equal probability of getting chosen, right? So now I've placed my first point. So now I only have n minus 1 more points to place, right? And by the time I place a second point, there's going to be n minus 2 more points to place, okay? But here's what I actually want to do. I want to look at this first point that I've placed, and I want to make a semicircle starting at this point, okay? So what I'm going to do is create the semicircle, right? And I want us to be able to see that the semicircle is going to span from that point, and it's going to go clockwise around to the other side, okay? So if we were thinking about this like a clock, we could call this 12 o'clock, and we could call this 6 o'clock, and we could call the semicircle that we want to examine the clockwise rotation from 12 to 6, starting at this point, which we'll just call point 1, okay? So let's place our second point. Wouldn't you agree that there's a 1/2 chance it's going to end up on this side, the side that we want, and there's a 1/2 chance it's going to end up on this side, right? I mean, we've cut the circle in half. It's clear to see that it's either going to end up on this side or this side, and it's going to happen both with probability 1/2. So there's a 1/2 chance we place our next point on this side. So let's place it. Okay, so we did well. We placed it, right? We got this side of the semicircle we wanted. And now, after that, there's n minus 2 points remaining to be placed, okay? And let's say we just go through this whole process for all the n minus 1 points that we have after this first point is placed, okay? That would mean that there is this 1/2 chance, and it's multiplying by 1/2, right? Because every single time we place another dot, we're taking another 1/2 chance. So we're multiplying it by n minus 1, okay? So you see that when we start with this point here and we draw its semicircle, the probability that the rest of the points placed are going to fall in this semicircle is 1/2 raised to the n minus 1, okay? Because there's n minus 1 points to place after this first guy, and they all have a probability of 1/2 of ending up in this right semicircle. Okay, so let's see how this applies to the problem now. Okay, so you may have seen where the logic is not fully complete, right? We looked at the semicircle formed by this first guy, right? And we said that after its, other n minus 1 points are placed, there's that 1/2 raised to the n minus 1 power that, all those points are going to end up in the same semicircle. But what if we wanted to start at the semicircle that was formed from this point, right? Or this point, or this point, right? So if we started from the semicircle formed by this point, okay, it would look like this semicircle, okay? And I might not split it in half perfectly here, but you get the idea, right? It would be this semicircle going around from here to here. But this is where we need to realize something that's fundamental to solving this question, okay? So if we call the event, right? So I'm just going to call these points. This is point I. Let's let this be point, we'll call this I plus 1, point I plus 1. This is point I plus 2. Bad 2. And this is point I. Oops. This is point I plus 3. Okay. So event I is going to be the event that when we form a semicircle in the clockwise direction from the ith point, all other points fall within that semicircle. Okay? So the event E of E sub I is the event that when we form a semicircle in the clockwise direction from the ith point, right? So event E of I plus 1 is this semicircle. Event E of I plus 2 is this guy's semicircle, right? All other points fall within that semicircle. And now here's where we need to dip into our probability toolkit, okay? These events, we have to realize that these events, okay, I'm going to put this in a different color because it's very important. These events are mutually exclusive, okay? Let's remember what mutually exclusive means. Okay, so what do I mean by that? What do I mean by mutually exclusive, okay? And it looks like I might have spelled mutually wrong, which is kind of embarrassing. What do I mean by mutually exclusive? I mean that no events, so event E and event EI and event EI plus 1 cannot happen at the same time, okay? None of these events can happen at the same time. And let's look at why that is true, right? So let's just look at event EI, right? That's this guy's semicircle, right? And now let's look at event EI plus 1. That's this guy's semicircle, okay? And do you see how as soon as we form the semicircle of the point I plus 1, we exclude point I? And if we were to go to point I plus 2, we would then be excluding point I plus 1. So because of that, no semicircles can be formed, or only one semicircle can be formed on this circle that will contain all of these points. And that's going to simplify things a lot for us, okay? So because we have mutual exclusivity, it allows us to do something that's going to make the problem a lot easier to solve, okay? So let's draw the union of all the events, okay? So the probability of event 1 happening or event 2 happening, or event 3 happening, or event 4 happening. Okay, because these are mutually exclusive, is the same as the summation of each of their probabilities. Okay, so that looks like this. And now this makes the question really easy because we already know what the probability of EI is, don't we? Isn't the probability of EI, isn't it just this 1/2 over, I'm sorry, 1/2 raised to the n minus 1 power? And so if we look at this summation here, isn't this just saying n times 1/2 to the n minus 1 power? Yes, it is. So then our answer is just equal to n over 2 to the n minus 1. And there we have it. Thanks for watching. See you in the next one.